Welcome everybody to this week's edition of HoloTube. We are very happy to have Francisco Peña Benítez with us today, and he's telling us more on fractons. Fran, the screen is yours.
Okay, thanks, Matthias. Thank you for the invitation. It's a pleasure to talk about our recent work. It's some paper that we put recently on the archive. It's in collaboration with Patricio Salgado Rebolledo, that now I realize that I forgot to add his name here. But okay, just let me start. Okay, so first, I will just let me just tell you more or less what the plan of the talk is going to be. So I will start with some brief motivation and definition of what fractons are. Then I will just discuss what the kinematics of systems that conserve dipole moments is, and then from that I will move to the conservation laws of and what the symmetry algebra associated to that group we have. And then I will just connect, or I will try to embed this symmetry algebra in the Poincare group. Okay. And afterwards, I will just propose I will take as a toy model some gravitational theory that will reproduce the type of gauge theories that we were looking for, and we will finish with some conclusions. Okay. So actually, when I was just finishing the talk, I just went to Wikipedia and I realized that actually there is a quite long article in Wikipedia that is just explaining what fractons are. Okay, so then I just copy some of the text. Okay, and somehow it describes very well what a fracton is. So a fracton, in principle, is just like an excitation that has a restricted mobility. Okay, in some cases, depending of the models, it may be allowed to move along certain subspaces of the full space, or it could be just actually it should be just forced to stay in a place and not allowed to move. Okay, so this type of systems or this type of excitations appear or start kind of appearing in this some quantum error correcting codes. Okay, and afterwards people realized that there is somehow a different class of systems that which are associated to the conservation of multipole moments and related to symmetric tensor gauge theories, which also have this type of fractonic behavior. Okay, actually, as you can see, the Wikipedia article has this sort of a long story describing all the classes of systems. You have this type 1, type 2, and some class of systems that are the gapless fractons. So I will focus just on this tiny corner here of the U1 scalar charge model, which is captured in this table by this. So the charges are characterized by scalar charge, okay, and the conservation of dipole moment, and the energy spectrum is gapless. Okay, so the systems that are kind of related to this quantum information and quantum correcting codes are this type 1 and type 2. I will not mention any aspect of this type of systems. Okay, actually, in previous oops, sorry, how do I go back? Okay, so in this previous slide, there was a sentence in the paragraph that I'm not sure, probably you didn't read, but I'm kind of zooming on this sentence where we find this interesting sentence that is saying fractons have also been shown to appear in quantum linearized gravity models and via a duality as disclination crystal defects. Okay, so basically, so these two aspects of fracton systems is kind of the main motivation I'm going to, or for me, is one of the main motivations to study these systems. Okay, so basically, so it recently by Predcorn and Rasikowski, it was discovered that you can kind of map the degrees of freedom in elasticity to one of these fractons gauge theory that I will introduce later on. But the important thing from the duality is that in elasticity, the fundamental degrees of freedom are just the displacement fields. Okay, so in principle, if you have topological defects on the lattice, then you can just split the displacement field in some kind of like a singular part and the non-singular part of the displacement field. So the duality works as typically this particle vortex duality works such that what is happening is that the topological defects, which are the singular part of the displacement fields, are mapped into what we are going to call fractons, okay? And the non-singular part of the displacement field is mapped into the objects that I'm going to call symmetric gauge fields, okay? And the whole thing is that once you map the elasticity theory into this fractonic gauge theory, what you obtain is some sort of generalization of electrodynamics, where the vector potential has been mapped into a symmetric tensor. Okay, so in this reference here, for example, you can just like find some examples of this elasticity fractons duality. So these are like some reviews where you can find like more details on like the whole landscape of fracton theories. Okay, and this aspect of the quantum linearized gravity has been just like discussed in this paper by Bretko, where basically he just compared linearized gravity with the gauge principle of these symmetric gauge fields, and somehow he compares with Einstein gravity and certain analogies in the behavior of the fracton systems. Okay, these other papers were focused more on understanding what happens if you try to put this type of gauge theories in curve space. Okay, because as we will see, there is some tension between curvature and the fracton gauge principle. So in fact, another part of like my motivation somehow is kind of, I mean, I'm using as my motivation kind of like the more provocative one, oh, sorry, what's going on? Okay, do you see my screen again, right?
Yes, it reappeared.
Okay, so my point is that I'm trying to use as a motivation as a kind of like a provocative point of view, because as I said, so there are certain puzzling similarities between these class of systems and elasticity, and somehow abusing of language, I could say that elasticity is a kind of like a non-relativistic gravitational theory, in the sense that elasticity is just a theory that is describing the deformation of elastic medias. Okay, and so in particular, if you want, for example, with a hexagonal lattice, just to tile around the sphere the lattice, you realize that it's not possible without adding topological defects. Okay, and here with this type of like a football sphere, it's made obvious. Actually, you cannot get like a sphere made of hexagons without adding these pentagons that are actually, from the perspective of this fractons elasticity duality. So these pentagons are precisely mapped to the fracton excitations. Okay, and then just like the gauge fields would be just like associated to the deformations of that sphere. Okay, it doesn't matter how large the sphere you want to get. So here there is another, for example, if you want to add just like millions of hexagons on the sphere, you cannot avoid having to add 12 pentagons into the configuration. Okay, so after just like having this very kind of like hand-waving or this like hand-waving definition of what a fracton is, and kind of like motivating one aspect that of the fracton theories is that at least is of interest to me, which is these similarities of elasticity and theories of geometry, to be kind of like more general and not being, because in particular we are talking about a non-relativistic system, so it's obviously not gravity. Now let me just try to be more precise, okay? And I start just to start defining exactly what do we mean with these dipole conserving systems, okay? So as I previously said, so the duality between elasticity and fractons, basically what it does is just maps disclinations, okay, which are point-like defects into fractons, which are objects that, as we will see, will not be allowed to move, and the dislocations, okay, that can be understood as a disclination, as like a bound state between a disclination and dislocations, are basically mapped into dipoles, into dipoles excitations via the duality. From like very long ago, it's well known that in elasticity, dislocations can actually move along the lattice, but disclinations are not. They are not allowed to move because basically, if you want to move a disclination, you would need basically to break the bonds of the lattice. Okay. What is nice about this duality is that this fact that these objects have this restricted mobility in the dual theory have a kind of like a clear and natural origin. And that origin is just related to the fact that for that system, the charge number, so the particle number, has to be conserved, but on top of that, the dipole moment of that quantity of the corresponding charge has to be conserved. Okay. For example, then just imagine that you have a translational invariant system that has the conservation of charge, and with this Qi I refer to the dipole moment. That in this precise example, you can imagine just dipole moment like Q times X, which is the position of the particle. Conservation of this quantity automatically forces X dot I to be 0. Okay, so then we immediately conclude that this excitation with charge Q is not allowed to move. Okay, however, if you just try to construct an object that is something like that has a charge, anti-charge, now with a dipole moment that should be a vector pointing in that direction, it's not hard to see that then this object is going to be allowed to move like freely, like over the space, because you can just, as long as you don't just like rotate the dipole moment, and you don't just change the distance between these two particles, then the dipole moment would be conserved and you would be allowed to have a free motion of this object. Okay, so this is kind of like an immediate kind of classical consequence. But from a more like quantum perspective, actually, we can conclude that the motion is, that this restricted motion is not like that solid, because, for example, just imagine this, let's just rethink again the case of a single particle. Okay, let's suppose that this blue cloud is a fracton. Then it's not like really hard to realize that if this particle emits a dipole, which I'm just like illustrating with this kind of like a bound state red-blue, then it would be allowed for this particle just to shift in space without breaking the conservation of charge and dipole moments. And if that particle wants to move again, a next step, it would need to emit another dipole. Okay, so then the only way for a fracton to move, or for this type of fractons to move, is by the continuous emission of dipoles. Okay, this is another example. For example, another example where we have just like two fractons of the same charge. Okay, and then we notice again that if these two particles just exchange a dipole, then they could just move in the following way. So this first particle can just emit a dipole, as we see here, and by the emission of the dipole, it can just shift in this direction. And then in the next step, if this dipole is just absorbed by the next fracton, then this fracton can move in the opposite direction. Okay, and then in the final state, we would have like the particles in different positions. Okay, so then somehow from quantum mechanically, this just from this kinematic perspective, strictly speaking, the particles it's not that they are not allowed to move; they could just have the certain motion via these processes that that I have introduced. Okay, so now I have just like assumed that we have a system with certain conservation laws. I mean, with certain conserved charges. And now the question is like, okay, there should be behind this conservation, there should be some symmetry. Okay, some continuous symmetry group. And this group, in principle, if it's not abelian, some like non-trivial algebra. Now the question is like, okay, what is that? Let's just try to see what it's going to be, what the conservation laws are and what the symmetry group is. Okay, for that we could assume that that we can just express the charges in terms of some local densities on top to the conservation of momentum and charges. I'm adding conservation of angular momentum. Okay, and then it's well known that if we have conservation of momentum and angular momentum, you will have a continuity equation associated to the conservation of momentum, where P is the momentum density and tau is the stress. And the conservation of angular momentum somehow is just introducing a constraint. Okay, that the antisymmetric part of the stress has to be some derivative of some object that is antisymmetric in the indices ij. Okay, in a similar fashion, it happens with the monopole and dipole charges. Okay, so conservation, if you require the time derivative of these two objects to be 0, you will obviously conclude that you will have a continuity equation for the charge, where this ji would be like the fracton current. But conservation of dipole will automatically imply that this vector current is actually not a vector current. It has to be the divergence of some tensor object, okay? Which obviously, if you plug this thing here, then you get this familiar fractonic continuity equation that probably you have seen already somewhere else. Okay, then you could just like try to see, for example, how if you just take those charges I introduced before, so this and how they are just and you assume that they just generate generate the symmetry group, then it's not like hard to realize that actually dipole and translations and momentum will not commute. Okay, they actually commute to the monopole charge. The rest of the brackets are just as expected. Okay, J. So the dipole obviously will not commute with angular momentum because the dipole is a vector, so it transforms accordingly. Okay, so then this is the symmetry algebra of the dipole conserving systems, and one of the first things we can observe is that it has same structure as a Carroll algebra. The only difference here is that so in the Carroll algebra, this Qj here is what is called Carroll boost. It's playing the role of the Carroll boost, and then this Q is what plays the role of the Hamiltonian in Carroll systems. The distinction here is that then the object we have here is dipole moment. In the right-hand side, we have charge. And if we have time translations, then the Hamiltonian would be just like a generator that trivially commutes with everybody. Okay, it's just like an abelian factor extra to the system. Okay, then we could like ask, okay, well, what happens if I just try to gauge that symmetry? Okay, to construct some kind of electrodynamics system. So the simplest thing you can do given the structure of the continuity equation, is that, okay, well, I can introduce some scalar field and some symmetric tensor field with the following gauge transformations. Okay, the scalar field has just like a time derivative, and the symmetric tensor has two space derivative. Then if I just try to construct some field strengths or electric and magnetic fields associated to these gauge fields that I just introduced, well, we could define the magnetic field in this form, and we could define this electric field, and they are clearly gauge invariant. And then this sort of like a generalized electrodynamic theory would be just constructed by the following kinetic term for the gauge sector, minimally coupled to the density and the current K that I introduced before in in this manner. Okay, we could, so since this is like a talk for a high energy audience, so then we could say, well, look, let's just try to write this thing like kind of like more compact covariant language. Okay, so well, we realized that we could do the following. Okay, we could define some f mu nu rho tensor with this defining this following form, where this A is a symmetric tensor field that is just satisfying this constraint. Okay, somehow this relativistic invariance that I'm just introducing, because I'm raising indices here with Minkowski metric. What is just breaking the relativistic invariance is just this constraint that I'm just introducing here. Okay, and in that case, then the gauge transformations are could be written in this form. Okay. Now, the whole story is that since as you can see, so the gauge transformations contains these like two partial derivatives. So then if you try to put that theory in curve space, these partial derivatives should be covariant derivatives, and then you immediately realize that you may start having some issues with the gauge principle, which with this slide, we can kind of like immediately just, we just naively, we say, okay, well, I have defined this A mu nu, okay, which is a symmetric tensor field. Now I define my field strength just like putting covariant derivative instead of having partial derivatives. And again, I just put covariant derivatives in my gauge transformations. Then you immediately realize that the field strength becomes not gauge invariant. Okay, because if you do a transformation of the field strength, that's the object you will get, and then you realize that you just generate the Riemann tensor, well, yes, the curvature tensor, when you do a gauge transformation. Okay, so a possible way of or a minimal way of solving the issue, if we would really want to put the theory in curve space, would be just like, okay, let's just write our kinetic term, and then I just subtract something that looks like a mass term that involves the Riemann tensor, but in such a way that, so the whole thing is that when you do a gauge transformation of this thing, okay, you will basically generate this term, and then by integrating by part, what you generate is the covariant. By integrating by part this term, you will generate this covariant derivative of the Riemann tensor. So which is telling us that there is a class, for this specific model, there is a class of backgrounds in which the gauge invariance is not broken, but somehow it's just suggesting that generically it's not going to be possible to have the theory like fully gauge invariant. Okay, so this is like an issue that that somehow different authors already pointed out in the past. But then we realized, so since this the symmetry algebra is just related to this, or is similar to this Carroll algebra, we realized that, okay, well, it should be possible to embed in a Poincare group this fractonic algebra. And then if we just start from some gravitational theory, after doing the contraction, in principle, we should just, if we start from something that is like completely gauge invariant, we should end up in something that is completely gauge invariant. So let's see what's happening, where the issue is coming from. I mean, why the theory in the end becomes not gauge invariant. Okay, so with this drawing, but I'm just like I will just try to sketch what's the logic of the contraction. So here I'm just like showing you what the Poincare algebra is. So we are going to assume that we have one extra dimensions. Okay, so this XA corresponds to the space coordinates, and this is the time coordinate, and this XN is just an extra dimensions that we are somehow introducing. So then the contraction is going to be defined as follows. So we are just going to the rotations between what we are going to call physical space and these extra directions will be just rescaled by a coefficient sigma that we are going to send zero. Like in the very end, this parameter is precisely playing the role of a sort of like a pseudo Carroll parameter. The difference in this case is that we are just, instead of The difference is that instead of sending the speed of light to 0, as you do in Carol, we are just doing the analog, but with a spatial coordinate. Okay. Then we rescale accordingly the translations in around this n direction. And since if you do that, then you would still get a relativistic theory on this space, on the space-time. But we know we don't want to have relativistic invariance. We don't want to have boost. This algebra that I showed you before does not have boost. And for that reason, then we introduce this parameter epsilon, which is allowing us to have like some sort of Aristotelian contraction of the group. And in the very end, what we will end up will be just like the time translations, rotations, and space translations. This object that we are that is just some components of the angular momentum. That is precisely what is going to, you will see that's what is going to become the dipole charge. And the momentum in the extra direction is what is going to be interpreted as the fracton charge. Okay, and this extra red generator somehow will decouple from the algebra and will not play any relevant role. Okay, after you take the full Poincare algebra and you implement the contraction, you will get basically this sector here that MDMA refers to momentum dipole monopole algebra, okay, which is this algebra I showed you before, the fractonic one. And then these extra brackets here that in the limit when sigma goes to 0 just becomes 0, okay, because this would be like dipole and charge. Somehow there's some sort of like a for finite sigma generalization of this MDMA. But in the limit sigma going to 0, they just these two terms goes to 0. Okay, and sorry, and this thing that I'm calling GA here, this is a typo. It should be actually K. Okay, it should be precisely this generator. So this is what the brackets of the extra generators are, but the whole thing is that this sector is forming a subalgebra, and so then we can just like decouple this whole. In the end, we will be able to decouple the gauge fields of this sector. Okay, so now that we have just like some scheme to generate some scheme to start from like Poincare, for example, if you can imagine Poincare in 5 dimensions, and then by taking some contraction, just get the algebra, the fractonic algebra we are interested in 1 dimension less. Then what we want to do is just to construct a gauge theory, okay, that will allow us to generate all this like a gauge theory I was just describing before. Okay, so immediately you try to do that, you will face several problems. So and then we realize that one of the main things is that the contraction is so singular that it's not really possible to preserve the invariance of the original invariance without the presence of some Stuckelberg field that is associated precisely to these rotations that are going to be the dipoles. Okay, so if I just come back here, so somehow when you send sigma to 0, the only way to preserve the symmetry of to preserve this sector of the transformations is just like by Higgsing in some way, by having some Higgs field associated to this direction. Okay, and that's precisely what this field psi A is just like doing here. This phi can be just like gauge fixed to be the coordinates of the space. So then just can you imagine these things are just the XA. Okay, so then this nonlinear gauge field that for the theory, then it's constructed like that, and it will have just this form where we could just like interpret these things as the Bilbines of this like larger dimensional space, and this is the spin connection. Okay, then the field strength for that gauge theory, as usual, should be computed as in this way, where this thing can be interpreted as the torsion of the space, and this is just the curvature. Okay, so then the next thing we need to do to construct the action is to define a bilinear form. Okay, we construct some kind of like a Yang-Mills type gauge theory, okay? And we introduce some bilinear form by requiring that it's just invariant under the SOD, 1 that is just in the very end preserved because the original Poincaré group is just broken down to SOD, 1. Okay, so then the most general bilinear form we can construct is it has this form. Okay, and then with these alphas like some arbitrary constants. So we take this bilinear form, we take this action, and now we do the rescaling of the generators, this rescaling with the sigma parameters, epsilon parameters, and then we send them to 0. Okay, with the peculiarity that the epsilon parameter that was associated to the Aristotelian contraction, we can freely send it exactly to 0. Okay, but in the process of like of sending sigma to 0, as you will see in the end, it's necessary to keep the theory up to the linear order in sigma. We cannot send sigma to 0 as we usually do when you want to do a contraction to derive Carolian or Bargman. Typically, that's what the people do. What is kind of like a different in our approach to derive the fractonic theory is that this pseudo-Carolian parameter cannot be sent completely to 0, because as you will see, if you do that, somehow you just trivialize the theory, okay? And you don't get any dynamics to the sector of the theory that is going to be associated to the fractonic gauge fields. But that probably will become much more clear once we see the form of the final action, okay? What I'm just like showing you here is how the gauge transformations look like once you have done the full contraction, okay? So then this A mu here is precisely associated to the monopole, to this U1 gauge field, that then is showing this shift symmetry, okay, that somehow will be related to this constraint that we saw between the U1 charge and the dipole current, because this parameter BA is precisely the parameter that is associated to the dipole transformations, okay? This new tilde field is the dipole gauge field, and then it transforms as a gauge field with respect to this gauge parameter BA, and this theta are just like the rotations parameters, and it transforms as a vector along this index. The Stuckelberg field that we introduced, then of course it transforms as a Stuckelberg with respect to these dipole transformations. Okay, and then the field strength associated to dipoles, it looks like that, where this D is a covariant derivative that is constructed with the spin connection. I'm not showing the precise form, but it's just like standard covariant derivative containing the spin connection in it. And this F tilde is what it would be the field strength associated to the monopole. Okay, you get just the dA, and you have this mixing term with the dipole that is coming from the non-trivial bracket between momentum and dipole. Okay, so then I'm just kind of like going like really fast on the intermediate steps, because it's like quite lengthy and it's not particularly illuminating. But what it matters is that once you take the contraction limit, then you realize that your action will have a term that's going to be of order 0 in the sigma parameter, and then the sigma square term, something that is of order 2 in sigma. The zeroth order in sigma term contains only the gravitational sector of the theory. Okay, what we get is just something like the Riemann square, this torsional term square, and well, this is like a special torsion, and this is kind of like a time-like torsion. We get all this sector. So then you immediately see that if you send sigma to 0, you would kill all this term here. That is like actually the interesting sector, because it's the one that is accounting for the presence of the dipole gauge fields and everything. Okay, but then of course, I mean, that's the whole thing. So sending sigma, you send sigma to 0, but it's kind of like you are doing expansion for small sigma, and since the sigma is not exactly 0, then this is not allowing you to somehow to preserve the whole invariance. And then here it becomes kind of like clear that the Stuckelberg field appears in some special combinations with the field strength and the gauge fields in such a way that the whole thing is invariant via this nonlinear realization of the symmetry. Okay, but okay, this whole action is kind of complicated, so let's just try to understand it case by case. Okay, so the simplest case we can consider is like, okay, this alpha 3 was one of the constants that was associated to this torsional part. If we set this alpha 3 to 0 and you just restrict to flat space, we basically recover Predko's theory, provided you impose the following things. Okay, there is a possible gauge fixing of this gauge field A, which is basically set all the space part to 0. Okay, that's a gauge fixing that is allowed. And once you do that, you realize that actually this term with alpha 1, what is really doing is introducing some massive degrees of freedom in the system. Okay, so then setting this F tilde to 0, what it's just doing is just kind of like removing the massive sector of the theory and just keeping inside the theory the massless sector. Okay, then imposing, since this F tilde is something that combines the gauge field A and this gauge field V, solving the constraint F tilde equals 0 is kind of similar to what you do in GR when you just like force the torsion to be 0, that it fixes the spin connection in terms of the Willmans. Okay, if you remember actually the origin of the gauge field we have here, A is precisely the Willwein in the transverse direction, and V is just some components of the spin connection. So then imposing F tilde to 0 is some kind of like torsionless constraint that we are imposing in the theory. Once you do that, then the theory reduces exactly to the action I have derived at the very beginning for this fractonic gauge theory. Okay. On the other hand, if we just keep this alpha 3 coefficient non-zero, but still in flat space, what we just get is some kind of like a Proca theory for the system. Okay. So in the alpha 3 case, all the Goldstones just disappear, all the Stuckelberg fields just disappear from the theory. But if you keep alpha 3 non-zero, then you get this extra term that is just like a Proca-like term that is just giving a mass. Just what we have done is just redefine this alpha 3 in terms of, we call it M here. Okay, and this is just giving a mass to the gauge field A. Okay, more interestingly, we can just like then rescale all these coefficients alpha 0 in the proper way, such that what I was calling zeroth order action and first order action become both of them like zeroth order. In other words, we are just reabsorbing this sigma square into this alpha 2 and alpha 1. And then we get a theory that contains the whole gravitational sector. And again, this fractonic part that contains the Stuckelberg fields. Okay, and the whole theory is fully gauge invariant provided you are in some kind of like a Higgs phase. Okay. Now the thing is, okay, let me just come back 1 second to the lengthy one. Okay, so as I told you, so we were just kind of like understanding the sigma squaring principle as some perturbative parameter. So we could just imagine that in order to solve for the theory, we just need, okay, we just like set sigma equals 0 and you solve for the background. Okay, you find the background, and then once you know what the background is, you just plug it in S2 and you solve for the equations of motion for S2. That is somehow just like starting to construct solutions like perturbatively in sigma. So from that perspective, so this sort of hierarchy between the S1 sector and the S2 sector is just telling us that we could just like, okay, solve for S1, find solutions, put S1 on shell, and then treat in S2 the gravitational sector as a background sector. If you do that, you actually recover the action that we just like kind of like naively were just constructing from this by just analyzing how the field strength transforms. Okay, we just get our kinetic term with F squared and this part that contains this A gauge field here now refers to is precisely my V gauge field that I had before. The only difference is that here we have just imposed already the constraint that this we have imposed a constraint that this small f is 0. Okay, so basically A corresponds to the dipole gauge field that satisfies that solves the constraint f tilde equals 0. Okay, and then so actually that was one of the equations of motion of this gravitational sector. So if you find if you take variations with respect to the spin connection of this term, you precisely obtain this equation, which is the required equation for S2 to be fully gauge invariant. Okay, so in other words, if you want to get rid of the Stuckelberg fields, then you could impose those constraints of the on the geometry. But again, so the whole message is that even though we started from, so we thought that we could start from a gravitational theory that was like fully gauge invariant, we should in principle just get to a theory that is invariant when you just do the contraction, and then you realize that there is an obstruction, and that obstruction is just coming from this from the process. When in the process, when you send sigma to 0, then this contraction is kind of like so singular that there is no way to really keep the full invariance of the system as long as somehow there is some sort of condensation. Okay, and then with that, I just that brings me to the conclusions. So one of the messages that I would like you to take home is just like first, that indeed, as people have been pointing out, like recently, dipole conserving theories are intimately related with chiral theories. So actually, the way to generate that, I mean, we have proven that it's possible to generate these gauge fields by doing some kind of like chiral-like contraction of the symmetry group. Okay, with an important difference that, as far as I know, in the chiral literature, people is not like applying. So in the chiral literature, people send the speed of light to 0 exactly. Okay, and I wonder whether doing some kind of like analog contraction would give you some kind of like more rich dynamic for these chiral systems. I don't know if there are some chiral specialists in the audience that give me some feedback. So yeah, as I said, then it's like really necessary to have this Higgs field in the theory if you want to preserve the full invariance of the theory. Somehow that's just like explaining, as I mentioned before, that why there is such a tension between the fractonic gauge principle and diff invariance and curve space. And actually so yeah, just let me just like point out again something else. Typically, for example, if you just take which is something that chiral people do often, when they take just like some matter action, like some scalar field or whatever, and then you take the contraction limit. So when you send sigma to 0 exactly, then typically you get just like kind of like a trivial theory, okay, which is just like phi dot square or something like that, without any special gradients. So I don't know if that's just an artifact of somehow a similar artifact to what is happening here, that actually the dynamics of the theories are not going to be trivial if you just like keep in mind that you cannot really send to this parameter sigma to 0 exactly, because there are some issues when you are just taking the limit exact limit sigma going to 0. Okay, so well, with that I conclude, and now if you have some questions, here I am to answer.
Thank you very much, Fran. It was a very interesting talk. Who would like to start out with a question? I see a lot of hands clapping. So far, no hands raised. Oh, Kevin, go ahead.
Hello. Hi, Fran. Thanks for the
Hi, Kevin.
talk. Could you go back to the slide where you have the MDMA plus coming from Poincaré, and I think you showed there was a perfect. Yeah, where from here is would be the algebra between, is it PA and QA or PA and QB that I'm most interested in? Is that the one that's supposed to be Q delta AB?
Say again?
Is it the algebra between PA and QB that I would be kind of most interested in? PA QB is equal to Q delta AB. Is that the would that be the momentum dipole part of MDMA?
Yeah, so I have
I guess
so
I'm
the
mostly
things that are
concerned with
sigma, so the things that are sigma independent, that somehow I wanted to sketch it in blue in the diagram would be, so then I will have like what I
okay.
wanted.
They just work out.
I will have what I wanted, that is just going to be this.
Perfect.
Okay.
There's no,
So
there's
all the generators, yes, all the generators that are inside this MDMA, which is like dipole, that has dipole momentum giving me Q, is completely sigma independent, and then of course angular momentum with translations and all this, the rest of the brackets all are also sigma independent. Okay, so that the whole thing is that in the very end, so even though we have these sigma squares here, that somehow you could tell me, okay, well, but you are not sending sigma to 0.
Yeah.
So then you don't really have MDMA. So, but what really happens is that whatever this thing is contributing into this action that I was calling S2 would be of higher order. Okay. Because this factor, this S2 term comes with a sigma square in front, that is just coming from the metric basically. And then inside of the gauge field, whatever sigma square correction you get actually shifted to the sigma to the 4 correction. Okay, and then if you just stick to sigma square terms, you are like, what you are really preserving is exactly like the MDMA transformations, which are the ones I showed below with these transformations of the gauge fields.
Okay, but has this algebra been studied actually for finite sigma? Like, I've never seen this algebra actually in my life, so I didn't. It's not
I think it's
in
new.
every algebra. Yeah,
no,
I
think it's new.
Interesting to know the representation theory of this algebra.
Yeah, I have no idea. I think, yeah, I've never seen it either. But I mean, that's the whole thing. I imagine that if you just like take Carol and you keep this sigma square parameter, you should have similar factors.
Well, the thing with
because
Carol,
actually all this sigma sector is just identically as Carol. The only difference is that in Carol, it's just time, what you are kind of like the time direction that you're contracting here is just this extra space direction. But the structure is the same one.
But in Carol, you don't have these two, you don't have the analog of an epsilon and a sigma. There's no two things that you're kind of trying to send to 0, or maybe there's an obstruction to sending 1 to 0. So like, I mean, for Carol, if I were, that's to answer your question, and at the end, in Carol, if I had a speed of light and I weren't actually going to send C strictly to 0, then I would have usually just thought, well, then why don't I just rescale space to set C equal to 1? If C is not exactly 0 or infinity, then I ought to just be able to scale it. The what's interesting here is that you have two parameters. So if you send 1 to 0, then I can't just arbitrarily rescale sigma away, right? But
yeah, that's
really
that's right. Yeah, that's right.
Thanks.
Thanks for the question, Kevin. What other questions do we have? Maybe I can throw one in there. It's just I lost track around the slide where you explained fracton gauge theory from a non-relativistic limit of gravity. That's this you use a TA. Yeah, there. So the could you say again what the TA is?
So TA is like the field strength of this object. So
it has two other indices, right? It's a TA mu nu or something like that.
Yeah, let me just write it down. Okay, so TA is going to be DEA plus omega AB EB.
I see.
Okay,
And
it's the torsion field.
That's what okay, that's what I hope you would say. So what's the source for the torsion? So yeah, I mean, I'm just saying it from the Einstein gravity, you obtain that torsion is equal to 0 as one of the equations of motion, I believe, for the spin connection when you write it down in first order formalism, and just trying to understand where is this. So that means you have to introduce some source field that sources torsion in Einstein gravity. So add something to Einstein gravity. So I'm asking myself the question: what is sourcing torsion here?
Yeah, well, the difference is that we don't have Einstein gravity. That's just a consequence of the theory we are using. Since you have this Yang-Mills-like theory, and with that specific bilinear form that we are using, so then this t-square term is allowed because somehow we have this. So the metric that we are using is allowing to have like this PP to be eta, and that is going to be responsible of having this t-square in the action. So in Einstein gravity, you don't have that because Einstein gravity is not of the Yang-Mills form.
I see. Okay, thank you. Other questions? Sorry, I didn't want to derail the physical discussion by nitpicking.
Hi, Fran.
Hi, Carl.
Actually, it's a follow-up question to Matthias. So I'm getting confused a bit about. Can you go to the previous slide, please? Yeah, this one. So if I'm naive, can I think about the dimensions of the fields? For example, the gauge field A is does it have like, I would guess it has sort of a dimension 1. Can you assign dimensions to this? Where I'm going is the field bind typically, I think of something as being, dimension 0.
That's right.
So how can one assign dimensions to the fields here?
Right. I mean, I'm not going to, it's not a rigorous answer to your question, but the point is that, so I think physically what you are doing with the parameter sigma, so it's kind of like a, so because, yes, okay, when you rescale that coordinate, so then you end up basically having a coordinate that is a dimensional because you want that quantity to be basically the phase, okay? And sigma is what is going to give dimensions to the gauge field, because sigma is going to be basically like the units of the dimensions of the charge.
Okay. I think this explains, because usually when you try to just doing gravity, interpret the field line as a connection for the translations, you run into quite some problems, and you actually do have to introduce an additional scale in order to make that work, to connect the field to a gate field. But here it's sort of automatically built in, and it's the sigma parameter. Did I understand that?
Yes, exactly. That's what I meant.
Okay. Thanks.
More questions? Okay, so if that is not the case, I don't see any more hands. We have like a 5 minutes of informal chat after we close the session. But before we do that, I would like to remind everybody that next week, on Monday, note the different time slot, we have a discussion on causal and stable hydrodynamics, and we have 2 groups contributing to that, from Chicago and from Victoria. So Pavel Kovtun and his collaborators will be there, Akash Jain, and then George Noronha and his collaborators. And we are looking forward to see you all at that discussion. Again, that's Monday in a different time slot. Just be aware of that. Okay, so with that announcement, and I would like to thank Fran again. Thank you very much for this interesting talk. And thanks everyone for the questions, and I hope to see you next week.
Thank you.